Hello, everybody. Welcome to a new lecture of information retrieval. So first, I have to say that we forgot to activate the recording in the first hour of today's lecture, so that the recording is not available. However, I am now recording it again so that you can also see what we have been doing this morning if you're watching the recording. And just so you know, there is also recordings from previous years. For example, last year, if you want to watch a live lecture on the same topic. All right. First, a quick recap of what we have seen so far. So we covered the Boolean retrieval. So we see that if the collection is a set of documents, we have a query language that allows us to retrieve a subset of these documents based on and, or, and not. We saw that in order to implement that efficiently, we can use a structure known as the standard inverted index with the dictionary on the left and the posting list on the right. We saw that the dictionary has an underlying data structure, which can be a hash table or a B+3. Hash tables are instant, B+3s are logarithmic, but have the additional benefits that they can handle ranges of queries, which is useful for wildcards, for example. Then we saw that we can have more kinds of queries, including wildcard queries at the beginning, at the end, in the middle, both at the beginning or at the end. We saw that we can also do some spell correction by automatically looking for close words. And finally, we have phrase search, where we can put a sentence, a whole sentence, with the order of words being important between quotes. We saw that for this phrase search, we need additional structures, so that expands the standard inverted index. One of the ways, the byword index, where we have these sliding windows over the text with pairs of words that appear next to each other. Of course, this is a bit larger as an index, but it allows you to handle some phrase queries. And the alternative way to handle such queries is to have a positional index, where we still have single terms on the left. However, we extend each posting with the exact positions at which the term appears in the document, together with the number of times it appears. So for example, 2 appears 3 times in document C at positions 4, 7, and 11. We saw that we can use trigram indexes in order to respond to wildcard queries or do some spell checking. We saw that we can also map terms to term IDs, because in a standard inverted index, we know that a posting is a pair of a term in a document. The document is just an ID. And in the index, the term is always the same on the same row, so we just put it once on the left. But when we build the index and we produce these pairs in memory, that might repeat a lot. So we can replace terms with a term ID to keep the pairs shorter in memory. And this is what the blocked sort-based indexing algorithm is doing, BSBI, which processes the collection in batches, produces all the term ID, document ID pairs, and then puts them back to disk. And then at the end, we merge everything and build the index. Then there is a second generation algorithm known as SPIMI, or single pass in memory indexes. In that case, instead of producing intermediate key value pairs, we directly produce partial standard inverted indices that we spill back to disk, and then at the end, we merge them in linear time. We saw that in real life, the collection might actually change over time. So one way to handle this is to have an auxiliary index where we have the most recent changes, and then we have the main index that remains the same over longer periods, and we periodically merge the auxiliary index to the main index. And we saw that there is an efficient way to merge existing indices with a logarithmic approach, similar to the 2048 game, where we try to do a logarithmic number of merges, every time doubling the size of the indices. So this is known as logarithmic merging or log structured merge trees, LSM trees. Then we saw that if we keep adding documents to our collection, the number of terms is going to keep increasing as well, the number of distinct terms, and that increases in the square root. So that is a surprise because we might have expected something with a horizontal asymptote, but that doesn't happen. So if you keep adding new documents, the number of terms keeps increasing, even though that increase slows down over time. So this is known as another tongue twister, Hipp's law. And it's causing Hipp's law means that if you rank the terms by their popularity, meaning the number of times they appear in a collection, also known as collection frequency, then if you rank them by decreasing popularity, then the frequencies go in 1/n. So some constants divided by the rank. So it's a hyperbole, and that's Hipp's law. We saw that we can compress the dictionary in memory. This, for example, is what is called front coding. So it makes it less space consuming than if you would just store all the terms. And we saw that we can also compress the postings list on the right. The first trick is to encode the gaps rather than the document IDs themselves. And that is because the document IDs are in increasing order so that the gaps are always positive. But the problem with that is that the size of the gaps might vary a lot. So we need something elastic that can automatically shrink for small numbers and grow with large numbers. This is a problem that has been solved by Peter Elias of MIT a while ago, known as the gamma encoding, which encodes every number by suppressing the leading one and replacing it with a sequence of ones and a zero according to the thermometer encoding of the exponent in base 2, of the logarithm in base 2, and that gives us the gamma code. The way you recognize a gamma code is that it has an odd size with a zero in the middle, only ones on the left, and then the base 2 representation of the number without the leading one on the right. We saw that the gamma encoding is optimal for absolutely any distribution of the input, which is very, very remarkable, within a factor of 3. So this is called a universal encoding. If you take, for example, the thermometer encoding, it's very bad for most of the distributions, but it turns out that the thermometer encoding is optimal for geometric distributions, negative powers of 2, but it's not a universal encoding because that's pretty much the only distribution that the thermometer encoding is good for. But the gamma encoding within a factor of 3 is optimal for any distribution. That means that it's within a factor of 3 of the entropy of the distribution, which would be the optimal size, theoretically. What I haven't shown you last time is what effect it has to use a gamma code, and it's actually improving by a factor of 4. So if you would store all of the postings uncompressed on 32 bits, that would take 400 megabytes for a collection of 1 gigabyte. But if you use the gamma encoding of the gaps, then that's actually shrinking it to just 100 megabytes. So it means one of two things. Either the index takes less space or memory, or you can fit 4 times as many documents with the same amount of index memory. I strongly recommend that you read chapter 5 on index compression as in every week, because in case what I'm telling in the lecture doesn't make any sense, then you can actually get another angle from the book. All right, and now we proceed to this week's topic of interest, which is that we are moving from querying with a Boolean query looking for a subset of documents to a newer kind of system where we are actually organizing the results in a ranked fashion. So imagine that in the old system, I return 1 million documents and you throw 1 million documents at the user. They wouldn't even know where to begin with these 1 million documents, right? But if you rank the results, then you can return the top 10, for example, as is commonly done with Google, Bing, or DuckDuckGo or other search engines. And that requires a way to rank the documents, which is what we are now getting to. A first approach to ranking is based on so-called parametric search, and then I move on to the second approach based on the vector space model. So in this first approach, we basically consider still that documents are sets of words and can be encoded as vectors of Booleans. However, we add something which is the metadata. And actually, if you go to a library or you look for books online, you will notice that it's not just the full text of the book, it's also the title, the authors, the publisher, the number of pages, the language, and so on and so on and so on. That metadata, in fact, is very valuable, and you can even offer a user interface to specifically search by metadata. But you quickly realize that the problem of looking for the documents that match this query is a relational database problem, really, because you can consider the metadata to be a relational table, and every query entered in the form can be transformed to a SQL query, which is a simple filtering query on the fields. And it turns out that in relational databases, we know how to improve these queries and make them fast, and this is done with indices, surprise, hash tables, B+trees, but this results in a very classical null-Arthur-Stein implementation that you saw in DMDB, which almost all of you attended already. And it means that we built index structures as is done commonly in SQL databases, and we use them in order to retrieve the resulting documents in the form of records. However, if we also include the full text of the books, we can not only have these SQL indices that you see on the top of the slides, but also the standard inverted index with the contents of the documents. And then you have something that is hybrid between good old relational database and an information retrieval system where you can combine a query on the metadata with a query, a Boolean query on the full text of the book. It turns out that this kind of search can be used to give a prototype or a simple way to rank the results. And the way you do that is by realizing that you can also have full text search on fields like title, author, and that means that you can also have an additional standard inverted index. So in that case, not only the actual contents, the terms, but also the title, the author, could be indexed with a standard inverted index. So now you end up with 3 standard inverted indices plus the traditional SQL indices on the top. Now we can merge these, right? Why don't we merge these standard inverted indices in a single shared inverted index? Well, here's how. So let's make room on the left by extending a little bit the space for the terms. And I'm going to add to every term the zone to which it belongs. So the zone could be the contents, the body, the title, the abstract, the authors, and that tells us where this term is to be found in the documents. Now, if we have several zones, then we end up with something like this. So here I have the body and the title and the authors, and I have now a postings list for every combination of a term and a zone, right? That's number one, the first way of doing that. And number two, the other way, is to still have the terms on the left, but to put the zone in the postings instead of putting them in the terms. And then you end up with postings that contain the document IDs plus the zones in which they appear. So how do we use that in order to get scores? Well, here's how. When you have a specific term and a specific document, you can compute a score by adding weights for all the zones in which the term is present. So the weights would be in vector G, and S is a Boolean that says, yes, it is in that zone, or no, it's not in that zone, right? So the zone weights are in GI, and the Booleans are in SI. So what it results into is, in fact, that you sum up those GIs for which SI is true. It's probably did not escape your attention that this is in fact the dot product. So you can also consider that GI and SI are vectors, G and S, and that you're computing the dot product of these vectors. Very concretely, assuming that G would be 0.3, 0.2, 0.5, and that's 3 zones, title, abstract, and body, and we compute the score of document 1 for the query information, that gives us just 0.5 because 0.3 and 0.2 are multiplied with 0 because information is not in the title and it's not in the abstract. And if we compute the dot product, that gives us 0.5. If we do the same for document 4, for which information is in title and body, then we add 0.3 and 0.5 because 0.2 would be multiplied with 0 because information is not in the abstract. which gives us a total of 0.8. And finally, if we do it for body and abstract, then we are going to end up with 0.2 plus 0.5, because 0.3 is going to be multiplied with 0 because information is not in the title, and that gives us a score of 0.7. Now, if we get the scores for every document, which we've just computed, then we need to rank them and sort by score, and the best result is document 4 with a score of 0.8, then document 5 with 0.7, and document 1 with a score of 0.5. So we have now a first ranked retrieval system that is going to give us an order in which the documents are returned. We can extend that to support multiple terms, for example, information and retrieval. In that case, we do the same thing, not just for information, but also for retrieval. So we do that for every term. And then we not only add across the terms, but also across the zones, and we get a grand total over the 2 dimensions of 1.3. I would like to note that this can be done efficiently if you remember the intersection algorithm that is used to implement the conjunctive queries, and we can extend that so that at the same time we compute the intersection of the posting list, we also compute the dot product by adding the information for the terms, right? So we can compute this dot product dynamically as we proceed through the documents to compute the scores, right? So for example, if you process at the same time information and retrieval and you're at document 4, then you are going to add all of that together from information and from retrieval to compute your grand total. This in fact has a name. It's called evidence accumulation, because we accumulate the scores on the fly as we go through the posting list. It's important, and I'll come back to it later, because that's also going to be important for the vector space model. Now, I would like to open a small parenthesis to make a bridge to the Introduction to Machine Learning course, which roughly half of you are currently taking, because we need to decide what that vector G is in order to decide the zones, right? I put this 0.3, 0.2, 0.5 completely arbitrarily, but we can actually figure out what the optimal values are. And when I say optimal, then you probably start thinking of machine learning. We could learn that. In order to learn, we need a training set. And so we are going to assume that we have a training set with plenty of queries, with every time a vector F of the zones that were activated by a specific term on a specific document, so vector of Booleans, plus R2, which is basically telling me yes or no, this was relevant to a human being. And that's actually something we did ask to a human being. So this is assuming you ask real people. And in that case, a human told us, query ETH on document A was actually relevant to me. And so R2 would be 1. So then with this training set, you can compute for every sample. So J would be the index of the sample, the dot product for that sample. And ideally, that dot product should give you it should be 1 if it's relevant and 0 if it's not relevant. But that would only be in an ideal world. That's not actually going to happen like that. We only want to be close to it, because that's only an approximation. And by close, we mean here the most classical method ever that you find in machine learning systems, which is the least sum of squares, where we compute the difference between the expected relevance and the actual dot product, and we want to minimize the sum of the squares. And if you do that, you can apply machine learning techniques like a stochastic gradient descent, or in some cases, exact results. In that case, you don't even need a gradient descent. In the case of 2 zones, you directly have the results. You don't have to learn that, of course, by heart. I'm just telling you, sometimes there's exact solutions. Sometimes you need to use specific techniques. So some of you are taking Intro to Machine Learning. Some of you, I asked this morning, are also already taking the Advanced Machine Learning lecture, which you're allowed to do in the 3rd years of bachelor. So it's very, very nice. And now you can make that bridge between the 2 lectures. Okay, parenthesis closed. Now I'm getting to the weights. and to another way of designing scores, which is using linear algebra. So I'm going to now just make a little change. Instead of sets of words, we are going to consider bags of words. What does that mean? It means that not only do I know which terms belongs to what document, I also know how many times each term appears in a document. And this number of times that a term appears in the document is known as the term frequency. For example, in document D, foo appears 3 times. It's a bag, so it repeats 3 times. Bar appears twice, and foo bar appears twice. I insist that the term frequency has 2 parameters, T and D. You can see it in the subscript. It depends not only on the term, but also on the document. If you take another document, it's going to be different. It turns out that we've already seen the term frequencies before, and in fact, we have seen them in the positional index. If you remember, in front of the positions, we also have the number of positions that the term appears. That was the term frequency. That is exactly the same thing that we are talking about right now, and you can see they appear for every term and every document. So we can try to use term frequencies like this to compute scores. So why don't we just add the term frequencies for one document across all terms? So we sum over the term frequencies. 5 plus 0 plus 2 gives us 7. 1 plus 4 plus 1 gives us 6. And that is going to give us a score of 7 for A, 6 for B. So A wins and comes in position 1, and B comes in position 2. But we can make an argument that that's not actually great, because if you look closer, you notice that the term bar seems to be rare. Of course, it's a very small sample, so it's a bit of an exaggeration, but it's rare on that sample because it only appears in B, but not in A. So you could argue that document B is very, very specialized in bar compared to document A. And here the thinking, and one of you gave the correct answer this morning, is that we can put weights on the terms and give a higher weight to bar because it's more rare than foo or than foo bar. Right? So then we can try a new weighting scheme that is going to be an improvement over this one. And now we have a cliffhanger, which we kept for the break, and you are now going to retrieve us live from the lecture hall right after the break. Thank you very much.